Welcome to the second video on conic sections. Here we're going to take a look at ellipses, including circles. Before you start this video is designed in such a way that you must know completing the square to be able to understand this video, and in general to be able to graph an ellipse or circle. It's also a skill you need. It's a very complicated skill and there's no information about it in this video. So you may want to, at this point, do some research on completing the square before you watch the rest of this. I have a video on that at my channel, Recilo Math, but you can also check it out in other places. So we're going to proceed studying conic sections under the assumption that you're completely comfortable completing the square. Here is an equation, and I'd like to graph it. Now, the first thing I know is that it's a conic section, or highly likely to be. How do I know that? Because it conforms to the general format of a conic section, as you can see in the upper right corner. Furthermore, I happen to know that this conic section is going to be an ellipse. You may have suspected that because the name of this video is ellipse. But how did I know it was going to be an ellipse? Well, it turns out anytime that a times b is a positive number, you're going to have an ellipse as your conic section. And if you compare the general equation in the right corner to the equation we're about to graph, you'll notice that a and b are both 1. And since a and b are both 1, a times b is 1 times 1. 1 times 1 is 1, and that's indeed a positive number. That was my clue on knowing that I would have an ellipse here in the first place. Well, now that I know it's an ellipse, I'd like to be able to graph it. But here's the problem. You see the 4, -6, and -12 in the problem? Those numbers alone don't tell us very much. In other words, we can't tell much about this ellipse when it's in so-called standard form, which is what the formula in the upper right corner is called. And when your conic section is in standard form, there's very little information you can get out of it, unless you know some very advanced tricks. So one way to get information out of it is to rearrange the format of the equation. Now, mathematicians have spent centuries developing a mechanism here. And what they've discovered at the end of endless research is that if I can get my equation to look like the equation on the right, you see the 4 number signs there? If I can get my equation on the left to look like the equation on the right, then those 4 numbers in that format and only that format will tell me a lot of information about this ellipse, and I'll be able to graph it very easily. But the challenge here is getting it into that format. So now let's turn our attention to getting our equation to look like the one on the right, with the 4 number signs in it. Again, if we can find those numbers, we'll be in great shape. Okay, so the first thing I did is rearrange some terms. You'll notice I put my x terms together. You'll notice I put my y terms together. And then I put the constant term on the other side. This turns out to be a very helpful step in getting the equation to look like what we want it to look like. The next thing that I do is I complete the square on x and I complete the square on y. And after completing the square, and that in and of itself is a lot of work, I get those 2 things. This may be a good time to pause the video, do the work yourself, do the research yourself, and convince yourself that you understand the completing the square component of this one problem. Assuming that you do, or that you've now done your research, let's continue. Remember, our goal is to get the equation to look like the one on the right side with the 4 number signs in it. So what I'm going to do now is add 4 and add 9 to both sides. And that gets my two perfect square trinomials on the left, and my constants all added together on the right. You'll notice 12 plus 4 plus 9 is 25. But this equation still doesn't match the one with the number signs in it. You'll notice that that equation has a 1 here, but my equation has a 25 there. Well, how can we turn a 25 into a 1? Here's an idea. Why don't we divide every term in the equation by 25? That's the same as dividing both sides by 25. You see, by dividing both sides by 25, the right side is now 25 over 25. And that, of course, is 1. So now I have a 1 on the right side of my equation. Now here's a valid question. Why do we need a 1 over there? What's 1 got to do with anything? Well, the short answer is you have to have a 1 there. The reality is mathematicians have discovered that if they get a 1 on the right side, they can get a ton of information about the ellipse. And when the number on the right side isn't a 1, mathematicians have discovered that you can't get much information from the equation about the ellipse. And so it's a very valid question, why do we need a 1 over there? And for most students, unless you want to research way deep into this subject, most students just accept, okay, that's what the mathematicians have determined, that we need a 1 on the right side to deduce information out of the equation, and so I'm just going to get a 1 over there. Okay, now notice I've got my equation into the proper format. Let's juxtapose them to take a look at them and see what we can discern about this. So here's what mathematicians have discovered. If you get a 1 on the right side and you format the rest of the equation exactly as shown, it must be formatted this way, with the exception of it's okay to have a minus, like the y minus 3. If you format your equation this way, you can immediately tell what the center of the ellipse is going to be. Now, the center of the ellipse isn't on the ellipse, but if we know where the center is, we'll be one step closer to knowing exactly how to graph this ellipse. And you'll notice that the center is at -2, 3, which came from the equation with the +2 and the -3. You should notice a sign change there. In other words, mathematicians have discovered that the x and y coordinate of the center will always be the opposite signs of the perfect square factors that are in the equation. So if you can see the colors here, the red, +2 changed to -2 and -3 changed to +3. Why is it the case that the center is formed out of the opposite signs of the equation? That's a very great question and a very long story, and something we are not going to delve into here. Most students are content to just accept, okay, I'll change the signs, because previous generations of mathematicians have discovered that. It's a great and interesting research project if you want to search out why. I think it's fascinating, but I don't want this video to be an hour long. So, now we know that the center is at this black dot here, -2, 3. Now remember, the center of the ellipse is not on the ellipse, but at least I know where the center is. That's going to guide me to some other important points on the ellipse. Now let's turn our attention back to the equation. Notice the purple 25 in the first denominator. Mathematicians have discovered if you take a radical of that number, or the positive square root of that number, which in this case is 5, you will have discovered something about the ellipse. Watch the graph here. Mathematicians discovered that when you take the radical of the first denominator, the one underneath the variable x, when you take the radical of the first denominator and say you get 5, that means you're going to have a point 5 spaces to the right and 5 spaces to the left of the center. In other words, the ellipse will stretch from one dot to the other here. Those are the far left and right extreme ends of this ellipse. Why is that the case? That's a long, long story, and I'll spare you the details. But if you'd like to research it, it's fascinating. Well, because of this discovery of mathematicians, I now know 2 points on my ellipse. And not only do I know that those 2 points, you may see them as red, are on the ellipse, but we know that they're the far left and far right endpoints of the ellipse. Technically, they're called vertices, but they're the far left and right endpoints of the ellipse. Now, look at the other denominator, which also happens to be 25. Mathematicians have discovered that if you take the radical of that, which in this case is 5, that will tell you 2 more points on the ellipse. Specifically, up 5 spaces and down 5 spaces will lead you to the top and bottom of the ellipse. In short, whatever number is under the y factor, square root that, take the positive square root, which in this case is 5, and that tells you that your ellipse will go 5 spaces above the center and 5 spaces below the center. So while the center is not on the ellipse, the center was crucial for us to find the top, left, bottom, and right of the ellipse. And now I can fill in my ellipse by just connecting those points, and I'm done. Oh, by the way, this ellipse here is also a circle. It is possible for ellipses to be circles. There are 2 kinds of ellipses. Circular ellipses, we call them circles, and non-circular ellipses, which are more oval-like. This particular one happened to be a circle. Now, do you remember me saying at the beginning, notice the top of the screen here. You may recall me saying, whenever a times b is positive, I'm going to get an ellipse. And that's true. A and b were 1 each one in this problem. But furthermore, how do you know when your ellipse is going to be a circle? Well, it turns out mathematicians have discovered that whenever a equals b, you will get a circle, which is an ellipse, but it's also a circle. Now, in this case, a and b are both 1, so the statement a equals b is true. I knew at the beginning of this problem, I didn't share it with you right away, but I knew this was going to be a circle. Now, it turns out when you know it's going to be a circle, you can do a little bit less algebra. Let's now redo this problem with the notion that we know it's going to be a circle in addition to being an ellipse. I would still do the same thing. I would put my x terms together and my y terms together and complete the square. I would still add 4 and 9 to both sides, yielding this as I had last time. So none of that would really change. But with the knowledge that I have a circle now, I don't really need to divide both sides by 25 and treat this as a non-circular ellipse, although I certainly can. A nice shortcut at this point is to say, oh, I can deduce what I need about the circle from the numbers positive 2, negative 3, and positive 25. As long as these 2 coefficients in front of the parentheses are 1s or blank, basically in this case, as long as we don't have non-1 coefficients in front of those parentheses, here's a great shortcut. You can read the center of your circle straight out of the equation, just like we did for when we were treating it as an ellipse, which it is an ellipse. So the rule about changing the signs from the factors to the center is still a discovery from mathematicians that we're going to deal with. But at this point, you don't really have to divide by 25. You certainly can, but the shortcut is just take the radical of the number on the right, and whatever that is, that's going to be the radius of your circle. And so if you know the radius is 5 and we know where the center is, if you think about it, isn't that enough information to draw the circle exactly where it is? If you know the center and you know the radius then it's no problem just drawing a circle here at this point. And in this sense, some students tend to not think of this as an ellipse. Circles are still ellipses, but they're special ellipses. And so if you want to treat this a little different and not divide by the 25 here, that's fine. Now let's take a look at a more complicated equation. This turns out to be an ellipse, which is not a circle. You'll notice that the a and b values are 9 and 4. 9 times 4 is 36. 36 is positive. So I have reason to suspect this is an ellipse. So in order to graph this thing, I can't get a lot of information out of it in its current form. I see that it's a conic section, and it's probably an ellipse based on the 9 and the 4 and all the other coefficients, but I don't really have any information about where this ellipse is or how big it is. So to get graphable, actual usable information, just like the previous problem, I want to get my equation into this format, which you see in the upper right corner with the number sign. Now to get the equation in that format here is a little bit more work than the previous problem, but still doable. What I've decided to do here is first put my x terms together, my y terms together, and my constant term on the right. This will ultimately make the math easier as we go forward. And now having put my x terms together and my y terms together, I could, if I wanted to, right now complete the square. And it wouldn't be wrong. But completing the square on the non-monic trinomials, in other words, because I have a coefficient of 9 and 4 here, it's actually going to be a little bit easier to not complete the square yet. So what I've opted to do instead is to factor out the 9 from the x terms and to factor out the 4 from the y terms. At this point, some students worry, what if the lead coefficient of the squared variable is not factorable out? Well, it's always factorable out. It may mean that you have fractions, but you can always factor out the lead coefficient of the x squared and the lead coefficient of the y squared. Now, it's not mandatory that you factor this out at all, but the reason I chose to factor out the lead coefficients of each squared variable is because it's easier to complete the square on the monic polynomials that we see here in the parentheses. So I'm now going to do the completing the square process, but I'm not performing it on the thing in its entirety, just what's in the parentheses. Notice what's in each pair of parentheses is a monic polynomial and therefore easier to complete the square. So here I've completed the square on each monic polynomial. Now may be a good time to pause the video and convince yourself that you've got completing the square under control, or to research how to do that before continuing. So now that we're ready to proceed, what I've decided to do next, remember the 9 and the 4 that I factored out? I'm now going to redistribute them to the polynomials that are inside the parentheses. Why would I bother to factor out the 9 and 4 and then redistribute them later, as I've done here? Well, it's not mandatory that you do it that way, but I find it a lot easier because that makes the completing the square portion less intense and less work. Either which way, I've now completed the square and I'm ready to proceed. So in order to get the equation to look like the formula in the upper right corner with the number signs, I'm going to add 144 to both sides and add 4 to both sides. And when I work out the right side of the equation, it turns out to be 36. I did that on scratch paper. And now you can see I'm a lot closer to matching the format that we're aiming for. But remember, for an ellipse to be graphable, at least in an easy way, mathematicians have discovered that you need a 1 on the right side of the equation. Again, why that's the case is a much longer story. Suffice it to say, for now, I need a 1 on the right side, and I have a 36 at the current moment. So I'm going to divide both sides of my equation by 36, thereby dividing each term by 36. And of course, as we know, 36 divided by 36 is 1, and I now have the 1 on the right side that I needed. But if you compare this bottom line here with the very top corner format that I'm aiming for, I'm still not there. Luckily, because of the factored nature of these fractions, I can reduce 9/36 to 1/4, and I can reduce 4/36 to 1/9. And after reducing, I no longer have coefficients outside of the parentheses. And now that I no longer have coefficients there, I have a complete match between the current format of my equation and that format which I was going for. And now that I have the format match that I need, I am now ready to graph this ellipse. Because having achieved that format tells me a tremendous amount of information about this ellipse. I'll remind you what you saw from the previous problem. First, we can deduce from the -4 and the positive 1 in the problem that the center will be +4, -1. Again, mathematicians have discovered that there's a sign change here required to find the center. Why that is, we won't go into. Suffice it to say, if you change the sign on the factors, you thereby have discovered the center of this ellipse. Now the center isn't on the ellipse, but knowing the center is 4, -1 is going to be very helpful. And we can now use the 4 and the 9 as the denominators to find more information about the ellipse. First, let's take the positive square root, or the radical, of the first denominator, the one under the x factor. Radical 4 is 2. What does that tell me about my graph? Well, take a look at the center of my ellipse. And what that 2 tells me is that the far right and far left ends of my ellipse are both going to be 2 spaces away from the center. And therefore I now know the far right and the far left extremes of my ellipse. These are actually called vertices, but I won't worry about the vocabulary right now. So I've used the 4, you may see it as a purple 4. I've used the 4 in the denominator to find how wide my ellipse is going to be. Because the square root of 4 is 2, each of the extreme left and right ends of the ellipse will be 2 spaces from the center. Now let's take a look at the 9. Radical 9 is 3. That tells me, take a look at the center of my ellipse, that there's going to be a point 3 spaces above and 3 spaces below the center. And that will give me the top and bottom extremes of my ellipse in the vertical sense. So now that I know those 2 points, I now have 4 points on my ellipse. But those 4 points, you may see them as red, those 4 points are enough to graph this ellipse. Because not only are they on the ellipse, they're the vertices, or the extreme ends of the ellipse. Once I've deduced those 4 points, I'm done graphing this ellipse, and there it is. And while there was a lot of algebra to get it into the proper format here, once I had my equation in the proper format, graphing became very easy. But it turns out, you'll notice as you go through this video series, that graphing conic sections is mostly about the algebra. And that concludes this second of 4 videos in this series. Thank you so much for watching.